Okay, I think we're rolling. Welcome, welcome. Let me go ahead and pull the chat up here so that I could see if anyone's there. Okay, hey, welcome. Yeah, another edition of the F word today. This is quite exciting. You know, sometimes we get involved in the nitty gritty of how to write specific kernels. Now that we've got like the majority of Spectra element library and Fortran together, and we're starting to build models, we're starting to see specifically where we're spending a lot of compute time, and so we're taking a moment to optimize some of those more expensive kernels. So yeah, this is some quite exciting stuff. That I did not do alone. Garrett at Fluid Numerics helped out a lot with driving some of the exploration of the different methodologies that I'll be talking about today. At any point, if you have questions, I am watching the chat. Go ahead and drop things in the chat. If you can't find the chat window, that means you need to subscribe to our channel so that you can leave us messages and we can talk with you. So let's go ahead and get started. So for those of you who don't know, I think many of you do know what Self is, but just to make sure we're all on the same page, Self is a library of Fortran classes. It's built with object-oriented Fortran. The goal is to help you build spectrally accurate conservation law solvers that can run on a variety of systems, personal workstations, multi-core platforms, AMD and NVIDIA GPU accelerated platforms, accelerated processing units or APUs, as well as supercomputing clusters. So we've got a lot of things that are baked into Self that allow you to do that, and we try to make it as simple as possible to write your own conservation law solver. Now, if you've watched these before, we've gone over that a few times, but of course, going forward, we'll continue to have tutorials and demonstrations on how to do that. In terms of what's relevant today, I do want to talk about what is at the core of Self, the way Self sees reality, the way it sees geometry, is using unstructured isoparametric meshes. And particularly, we use quadrilateral elements, so elements with 4 sides in 2D and hexahedra in 3D, so 6-sided elements in 3D. What this diagram is showing is in the background like a physical domain, some example of a physical domain in 2D. And if we zoom in a little bit here, you can see there's an element, one of these elements, which is a thing that has 4 sides. Inside that element, we treat the solution and all the geometry information as a Lagrange interpolating polynomial. Now that Lagrange interpolating polynomial has to go through a set of interpolation points. Now we choose, for spectral accuracy reasons, to use Gauss-like quadrature. So this can be Legendre-Gauss, Legendre-Gauss-Lobato. It can be Chebyshev-Gauss or Chebyshev-Gauss-Lobato. In practice, pretty much everything I do is on Legendre-Gauss, but the Self provides you options to pick which quadrature points you want to use. The other way Self sees the world, and now that we have this kind of general sense of how we describe geometry, what we want to do is cast a generic conservation law onto that geometry. And so the way we sort of abstract away a lot of things for you is to view the world in terms of this standard equation here. So we have the time rate of change of some prognostic variables, plus the divergence of a conservative flux has got to be balanced by some source terms. So the idea behind Self is that if you give me very simple functions, then in Fortran, these are pure Fortran functions that take in the solution variables, and you can turn around and give me a conservative flux. And same thing for the source terms. If you can write a simple pure Fortran function that takes in the prognostic variables and gives me the source terms, you can define a conservation law. Now, under the hood, all this guy here, the conservative flux, the divergence of that flux is really where all the work goes, is doing calculus operations on unstructured grids. This guy, surprise, surprise, is the most expensive. If you're doing hyperbolic systems where the flux depends on the solution, that's one level of expense. If you're doing parabolic problems where the flux depends on the gradients of the solutions, that's even more expensive because now you have to do gradients and the divergence. Certainly you can envision scenarios like in combustion, for combustion problems where you have combustion chemistry going on, or certainly your source terms can end up dominating. But at least in terms of the things that self is providing you out of the box, the divergence of the flux is the most expensive part. So we'll be focusing on that guy today. The way we do things, so we actually solve the equations not in the strong form, which is what you have here. We solve them in the weak form. And the way you get to the weak form is to multiply that conservation law by a set of test functions, and you integrate over space. And then you do integration by parts once on that divergence term. So you split the divergence operator into two components. On the left, you have the surface flux. So it's the bits on the boundaries of each of your elements. And then you have the volume flux. So anything in the interior of the elements. And because of how things work out, there's more points in a volume than there is on the surface. So the most expensive part of that is the volume flux. Surprise. And all this stuff has been borne out. We do see this behavior in profiles of a variety of our examples. So just trying to make the connections for you here in terms of where all the work is done under the hood for you, so you don't have to write it. So yeah, for the discretization within each element, the solution is again approximated by Lagrange interpolating polynomial. The interpolation knots are Gaussian quadrature points. Again, I primarily work with Legendre points, particularly Legendre-Gauss, but there are options for Legendre-Gauss-Lobato as well as Chebyshev Gauss and Gauss-Lobato points. Once you do that discretization, once you make these assumptions that the solution is a Lagrange interpolating polynomial and it goes to these quadrature points, we can convert this expression here. So the thing that's weighted by each of the test functions, and again, we'll make each of the test functions, each of the Lagrange interpolating polynomials, we can convert that continuous integral to a discrete sum. And that's what this ugly expression is here. So this thing might be meaningless to you, but let me walk you through one thing here. So we have three components of a flux vector. If you're doing three-dimensional operations, we have the x, for example, the y, and the z component. And in terms of how things are laid out in memory, within each element, you have three indices that you can use to index through the flux. So I have my I, j, and k directions within each element. If I take each component of that flux and do a matrix vector product with the appropriate dimension, I can get derivatives in each direction. So this first term, if I take this d hat matrix, is what we call the dg derivative matrix. That guy is what comes out if I substitute in for grad phi here a gradient of my Lagrange interpolating polynomials. My dg derivative matrix, if I do this summation operation on the first dimension of the vector, that gives me the derivative of the first component of the flux in the first direction. If I do this in the second direction, so I have my derivative matrix again, but now I'm doing matrix vector product, and now my summation index is this second dimension that gives me, so for example, this would be dfx dx, so the x component of the vector, we're going to take the x derivative of. This is the y component of the vector that we're going to take the y derivative of, and the z component of the vector we're going to take the z derivative of. Everything gets reduced down to this. In mapped coordinates, there's not much addition you really have to do, which is what I love about these methods is all we need to do is take things that are expressed in physical coordinates, so x, y, z space, and do the projection onto what are called the contravariant bases vectors. That's that first step. Then we do our divergence. That's the same thing I just showed you. It's a bunch of matrix vector multiplies. And then we have divide by the Jacobian of the coordinate transformation, and that gives me effectively my flux divergence. in 3D is what I showed, but we can follow the same thing in 2D or 1D. So I know that was like a very fast crash course into all this stuff. Now we do have all this documented up on our GitHub page. If you just go to self.fluidnumerics.com, we do have docs up there. There's a learning section in the documentation that goes over all of this stuff in detail, and we're still building it out because there's just so much information to put out there for you. I do want to change gears and talk a little bit about, like, the hardware that we're trying to run on. Particularly, we'll look at GPUs and how we characterize performance on those platforms. So let's go ahead and do that, because we're going to be talking about how do we implement this in code, and there's there's a million ways you could write that algorithm in code. A lot of them are not performant. And a good number of them are. And so in order to understand what's performant, you do need to know a little bit about the hardware you're running on. So the system we're looking at today, it's a super micro system. It's an older model. It's the AS4124GS. It's got two AMD FX 7313 16-core processors in it. We've got 4 AMD MI210 GPUs, so we're only half loaded. This system can actually fit up to 8 GPUs in it, but we only got it half loaded. And then the interconnects between each CPU and the two halves of our GPUs, they're connected via PCI v4 16 lane. For everything we're doing that I'll be talking about today, we are looking at ROCm 6.2 from AMD for providing us basically the HIP support for all of our kernels. And then the CPU side compilation's done with GNU Fortran 12.3. The operating system we've got on this currently is Ubuntu 22.04 with the Linux 6.8 kernel. In case you're interested, this system is on our cluster. If you end up wanting to become an innovator or the innovator class of collaborator with us through Open Collective, you get full access to this system, as well as the new MI300A system we've got coming up, and some V100s that we also run. But anyways, we're talking about GPUs. So when I think about performance, I always tell people to set realistic goals, and the same goes for when I talk myself and try to coach myself through doing some of this programming exercise. Always remember that if you want to do compute, you've got to be able to move memory you got to be able to move data from memory onto compute units. When you're done computing, that data needs to move off the compute unit back into memory. And just to give you, I guess, a picture representation of this, on the left side, I have a schematic of a fictitious GPU, but it's a good mental model to have. Your data sits out here in what's called HBM memory. And when you run a kernel, those kernels run their instructions on compute units, and then to get that data from memory onto the compute units, you have to go through an L2 cache and onto the compute unit. So the order in which you access memory is absolutely important. The types of memory you use in the memory hierarchy is important. But it's also good to know, if I move a certain amount of memory from HBM to the compute unit, how many flops am I doing on that? And that ends up determining what the peak performance is that you can actually get. So we typically think about the number of flops that you can do. There we go. The number of flops that you can do is proportional to the rate at which you can feed data, so the memory bandwidth that's available. If you happen to be in a range where you're not doing enough flops on that data. So what this looks like is we typically, you may have heard the term roofline diagram. Now the roofline diagram is not in practice, the kind of utility I've found with these guys is to really give you a good indicator of whether or not you're doing enough to squeeze the performance out of your system. That's it. That's all it's going to tell you. It's a really good way, because a vendor's going to tell you, here's my peak flops and all that stuff. None of that shit matters. None of that matters. Peak flops means absolutely nothing. What matters is what that system can actually do, sustained flops for one, and on the other side, your application, how it moves memory and how it does flops really is what's going to dictate what your limit is. So you have two types of applications. if I look on the x-axis of this diagram, we have what's called the flops per byte. It's called arithmetic intensity. It tells you for however many bytes you move out of a bank of memory and onto a compute unit, how many flops you're doing on it. That's a characteristic of your algorithm, in addition to a characteristic of how you implemented that algorithm. Now, the algorithm you may not have a choice on. If you've already picked that, then that's a given. So the only thing you have to influence arithmetic intensity is how you implement that method. You have on one side of this diagram, you have what are called memory-bound applications. So in this realm, the achieved flops per second, the compute performance, is a product of the arithmetic intensity and the bandwidth. And the more the higher your arithmetic intensity for your algorithm, the higher potential peak that you can achieve. Now, at some point, you in terms of arithmetic intensity, you'll reach the limit of what the hardware can do for floating point operations. And out here, you have what are called compute-bound applications. Their arithmetic intensity is so high, for every byte moved, you're doing so many flops that you're going to be bound above by what the compute hardware can actually do. Now, the majority of applications I come across in particularly in the PDE solvers realm, finite difference, finite volume, finite element, spectral element for that matter, all lie in this memory bound side. Now, what determines whether your memory on the other side of just your arithmetic intensity, this spot here where that transition happens, I like to call it the critical arithmetic intensity. Now, that point is a function of your hardware. It's going to be determined by a ratio of the peak memory bandwidth and the peak flops. Now, it gets more complicated than this. This is kind of simplified because there are different types of data. You can have FP8s, you can have FP16, FP32, FP64. You could be doing on GPUs vector fuse multiplied adds. You can do matrix fuse multiply adds. Different operations on different data types give you multiple different floating point peaks. So you can think of this diagram that has multiple horizontal lines in the compute bound region. And you actually have multiple levels of memory. We don't just have HBM memory. There's L2 cache, which gives us another diagonal. We have shared memory. We have, registers and all, so it gets a little bit more complicated. But this should give you an idea of like what we want to think about when we talk about characterizing performance. Because if I happen to be a memory bound application and my code is showing that it's getting a flops per second at a specific arithmetic intensity that sticks me on this roof of this diagram, I would not want to be fretting about the fact that my flops per second is not close to what the vendor advertised as the peak flops per second. That would be insane. You drive yourself crazy thinking that you can squeeze out more performance. At least the only thing you could do is think about ways to increase your arithmetic intensity, like by dropping your precision, for example. That's one way to do it. But at any rate, this is what I always think about is, one, characterize my application. Is it memory bound or is it compute bound? And once I know that, try to see how close I am to the relevant roof for my problem. Just don't want to drive myself crazy. Now, thankfully, oh man, I used to do this on an AMD GPUs. I used to do this with RockProf and a combination of like spreadsheets back in the day. I say back in the day, that was like 3-4 years ago, but it feels like a lifetime ago. You can use AMD's Omniperf to do this stuff. So like the results I'll be showing for our various kernels, we'll look at some Omniperf results so you can get a feel for how that works. We are about to look at code. I do want to make a plug, please. We love you guys coming here. This is even just showing up to these live streams is a way to support this project. Giving us a like on YouTube, subscribe to the channel, give us a star on GitHub. All those things are ways to support this project. Now, if you're able to, check out our Open Collective. We are looking for collaborators to help sponsor the project, as well as giving you, this gives you access to a variety of benefits. You can check all that stuff out on the Open Collective page. All right, let's look at some code. Before I show results, let's do that. Let's go ahead and look at some code. So, like I said, we've got this divergence kernel that we want to implement. What I want to do is show you guys how we do this on the CPU first, because that's pretty straightforward to digest. And then I'm going to switch gears and show you some ways we can do this with Bloss, because I've been told numerous times that, well, Joe, you're just doing Mat Mole everywhere. Why don't you just use Bloss? Why don't you just use Bloss? I got reasons why, but I tried. Like we went about trying it, and we did get some exciting results initially, but we found ways to do even better. But anyways, let's look at our I call this my naive kernel, because this was the way that I wrote it years ago, and it still is just reliable. So the divergence operator, what it's going to do is going to take, at least in 3D, it's going to take in a multi-dimensional Fortran array that's representative of our flux vector. And the way these are stored in memory is we have the first 3 dimensions are for the quadrature points within an element. Okay. So if I have 3D, if you think about sitting inside of a 3-dimensional brick, I've got an I, I've got a J, and I've got a K direction. And that gives me the first 3 dimensions. The next dimension is for the element that I am sitting in. So now if I vary the element, I'm moving around my mesh. And then you can have, the way we do things in Self is you can stack multiple prognostic variables in the same array. And then the last dimension is for each of the X, Y, and Z dimensions of your vector, right? So we have quadrature points, we have element, we have variable, and then we have the physical direction for our vector. The flux divergence is a scalar, but it takes on the same exact characteristics, except we just don't have that outermost dimension for the vector directions because it's a mathematical scalar. But it is a multidimensional Fortran array. So again, 3 dimensions for quadrature, 1 for element, and 1 for the variables. So what we do on the CPU side is we have a do concurrent loop. And we have I, J, K, so our quadrature points, we loop over elements, we loop over variables. Now, inside of that, this is where we do that reduction, where we're doing basically that matrix vector multiply across each dimension. So we have our derivative matrix that we multiply by the first component of the vector. And here you can see the indexing is over the innermost value. For the second direction, we index quickly over the next dimension, and then so on down the line. Now, I'll be honest, this is not an optimal implementation for a CPU, particularly because of this data striding that we're doing for the second and third components. There are better ways to do that, but we're still actively exploring improving the CPU side performance. But the point here is that you take away is this is what the algorithm is. This is the way it might come out if you look at it on paper and you just stick it in code in the most naive way possible. It works. It gets the right answer. Not the most optimal thing on the CPU, but everything we're going to be doing is riffing off of this. The other CPU implementation we're going to look at is actually splitting the 3 dimensions. Nothing crazy, but like if you think about an incremental approach towards doing an optimization on the CPU, we can split the part that does everything by stepping through memory sequentially. And then the next dimension we do separately. This is the one we'd probably do some loop reordering so that you get sequential memory access. And then same thing with the third one. But so this was just one step towards that direction. We haven't quite finished that out yet. But at any rate, that's 2 ways to do it on the CPU. So that's 2 out of our 6 that I promised I would do today. Now we have our Bloss implementation, which will require me to pull up an overleaf document to try to explain. Let's see what I can do here. All right. Us academics, we like to have slides and LaTeX and PDF documents, and all of our thoughts are strewn about everywhere. Okay. What I want you, I know a lot of this document talks about interpolation, but it's the same thing. If I just change my derivative matrix for an interpolation matrix, I can do interpolation. So it's kind of nice is the algorithm we're talking about can apply to a variety of things. So I did get a question from Nicola. Is Bloss better than intrinsic matmul? That I'm going to tell you is going to be dependent on your problem size. and highly dependent on your problem size, and it's going to be dependent on your what library is being pulled in. So that depends on your compiler, I suppose, for the intrinsic matmul. Is Bloss better than intrinsic matmul? It's problem size dependent, and I'll tell you, I'll give you a spoiler for us, because our derivative matrices are like 7 by or 8 by 8 or 16 by 16. They're real small. It's not Bloss is not great, but I know, to be honest, I haven't looked at intrinsic matmul for this particular problem, but in my experience, all these things are problem size dependent. Bloss particularly is really good at large matrices, so things that are like 100 by 100 or 1,000 by 1,000. But yeah, I don't know. I think it'd be worth exploring. At any rate, what I'm going to do is kind of walk you through a way you can break this out. And we'll do a one-dimensional example, but these ideas generalize to multi-dimensions. Actually, let me just go ahead and jump to 2D. So when we do things in 2D, what we have, so this F here would be representative. Actually, I'll stick with 3. I know I'm jumping around. 3D, because that's what we've been talking about. We'll do 3D. The thing that we're going to be applying a matrix to here to calculate our derivative is, in this document, it's this F right here. And then our first 3 indices, again, are our quadrature. So LP and Q are for quadrature. Alpha is for element. Beta is for variable. And then I have this summation where I'm doing a derivative matrix operation on top of that. Sorry, yeah, I'm doing a matrix vector multiply on top of that. So if I look at this carefully, I have an L index in the second dimension for my matrix, and I have an L for my first dimension if I'm doing my like first pass through doing that derivative matrix. So you can think about taking these like outermost dimensions and squashing them into one gigantic dimension. So I can convert that thing up here into a sum of my matrix subscript I comma L multiplied by FL comma R. So that first dimension I left alone, right? That's the same thing. That's still my first quadrature dimension, but then the R is like some combination of the remaining quadrature dimensions, my element and variable dimensions. And so F ends up looking like a matrix that has n rows and a whole bunch of columns, just real wide. That is perfectly suitable for GEM, G-E-M-M. That's the general matrix multiplication. Okay, so once you apply that, you can then unpack that guy. If you unpack that guy, now the next operation I want to do for the second dimension is to apply my matrix over this second dimension. So now I have my strided axis. So again, you can think about squashing down the dimensions after that again. Okay. And now you're going to do a series of matrix vector multiplies that are strided. So you're going to stride over that first dimension, and you're going to batch all of those. That is exactly what the hip Bloss or cuBloss GEM-V strided batched call is meant for, this kind of thing. The hitch is that I have to do a do loop over the starting points for each value of I. And I don't like that too much because that means a ton of kernel launches, which usually means some deal of overhead. But nonetheless, we can do that. If someone's really twisting my wrist to say, Joe, use a library, this is what I would do. I could be wrong. I often am. And if you feel like you got a better way to do this, I would love to hear your thoughts. All right, so we did this for the second dimension. We can rinse and repeat that same concept for the third dimension. Again, we're going to now do a sum over Q, which is the third dimension of F. Okay, so now we squash alpha beta dimensions, everything after Q, and then we do a stride where now we do a double nested loop over I and J to change the starting point for our strides. But again, we're still using hip Bloss GEM-V strided batched. Okay. Now, all of those things that I've just said are summarized in 3 routines that are provided in Self, just to give you some idea of where this is coming from. We have Self Bloss matrix op dim1 for 3D, so that's doing GEM. This guy is doing GEM-V strided batched. and this guy is doing gem v strided batch. And we have to do some fancy pointer arithmetic to make sure we're changing each of the vector dimensions we're looking at. So we just use Fortran pointers and cast things between C pointer and Fortran pointer, and life goes on. So that's our GPU Bloss implementation for doing a divergence. Everything else that we have are handwritten kernels. So I've shown you three things. I've got two versions of a do concurrent. I've got my Bloss implementation, which uses, again, a combination of gem and two batches of calls to gem v strided batched. All right. Now let's look at some of the kernels. Again, I can go to the most naive kernel. Now let me find that guy. And it's basically, if I took exactly what I had for my naive do concurrent. Let me actually pull these side by side. Let's go to our naive do concurrent. All right. So if you imagine you just stripped away that do concurrent loop and you replaced it with a CUDA kernel launch, or a HIP kernel launch if you're on AMD GPUs. If I replace that with just a HIP kernel launch and I only implement these instructions inside of here for each thread, that's essentially what our naive GPU kernel is doing. So I get my IJK, my variable index, my element index from the thread IDs from my kernel launch, and then I do my reduction for each thread. Right? That's what it looks like on the GPU if I do it in the most naive way possible. Now, there's some things I'm not taking advantage of if I do that. Like, for example, this derivative matrix is quite small. And if I'm reading him out of HBM memory and constantly doing this strided access like I am down below, from changing from I to J to K, that can cause some poor cache performance. I also have strided indexing over F, right? Because here this is actually contiguous for the first one, but the second one is strided, and the third one is strided. And GPUs have a special thing called shared memory that you can allocate for each block. And strided access out of shared memory is actually not that expensive. So one optimization on this guy is to go ahead and just move the derivative matrix and a small subset of this F thing into shared memory. If you do have questions on like some of the details, if I'm skipping over stuff, please drop your questions in the chat, and I'm happy to answer them. But what I do want to show you is if I take that kernel and leverage shared memory, what that looks like. So right now we're at 4 implementations, and now I'm going to show you the shared memory. So that'll give us 5 implementations out of 6. I think this is the one. Yeah, this is it here on the right. Let's go ahead and drop you back. Okay, so what we're going to do as an optimization to the kernel I just showed you is move, small blocks of the F vector into shared memory. And so what you do is initially, so I grab my indices from my thread IDs, which is not too hard to do. I've got my IJK, my variable dimension, my element dimension. Then I declare my shared memory. Now the way this is done is I actually use a template variable for the block size, which allows me to configure the block size based on the problem at compile time, which is quite handy. Because I wouldn't want to have a huge block of memory if someone's trying to do this with a small polynomial degree, so a low number of quadrature points. But if I have a large number of quadrature points, I want to make sure I'm allocating enough shared memory to work with that. So that's what the template variables allow me to do. So yeah, we're allocating shared memory for our for each component of our vector, so x, y, and z, and our derivative matrix. And then I load from HBM. This is all contiguous. All of this is contiguous loads. So I get nice coalesced memory access into shared memory for 1, 2, and 3. And then the little hack here is if k is 0, then I just use the INJ threads for k is 0 to load the derivative matrix. It's a bit of a waste of cycles there, but it's actually not too bad in the grand scheme of things. And then we call a sync thread. So basically by this point, all threads within the thread block have the same view of F1, F2, F3, and the derivative matrix. Now I'll add that when I do my kernel launch, there's a fixed number of threads per block. So 64 if your polynomial degree is less than 4. If it's between 4 and 8, we use 512 threads per block. And then the element and variable dimensions are done using the block IDs. So that's kind of handy. Basically, each thread block corresponds to a single element in your mesh, which I love this about Spectra Elements and how well it like adapts to GPU hardware lingo. Okay, so I've got these guys all in shared memory. Now I can do my reduction operation, but instead of using the variables pointing to HBM memory, I'm now pointing to the ones in shared memory, which again, as I said before, strided access and shared memory, yes, I'm doing them, but they're really not expensive. Strided access and shared memory is cheap. So we do that. All right. That's our 5th implementation. Now the 6th implementation is basically if I took those same ideas and just applied them to our split apart method, but where I have a kernel for each direction. Now, the one benefit of doing a split like this for 3D is that you may have, if you were careful in looking at what's going on here, in my naive implementation, because of my use of shared memory and because of some restrictions on the finite amount of shared memory I have per block, I'm restricting users to be up to only 7th degree polynomials, which someone might want to go higher order. The nice thing about having split kernels is that because I'm doing each dimension separate from each other, I can launch multiple kernels to do the full calculation. But I'm able to do my indexing a little bit different, use a lot less shared memory per kernel launch, and extend how many polynomial, like how high the polynomial degree can go. But so that's why we're looking at it. It's not necessarily something that would be faster. It would just be something that extends our usability to a higher polynomial degree. I'm going to go ahead and run this. Let me make sure I've got everything. I think I was using Rock'em 6.2. Yeah. Okay. And yep, I've got myself 2 GPUs. What I want to do, let's make sure module load GCC and make sure I got self up there. Okay, that's fine. What we're gonna do is clean it out. Did I not put in a make clean? I thought I did. Yeah, I did. I don't understand that. Oh, because I'm not in the source directory. Let's make the 3D benchmarks, and then we'll go ahead and run that. So basically what the benchmarks application is going to do is run each of those kernels. Let me see how big of a problem I set it up to do. So 2,000 elements. 7 variables, and I believe the polynomial degree by default is 7, so that's what we'll do, and let that run. So this will spit out, so one, I do have some like hand estimates for the amount of bytes that are read and written, as well as the number of flops that are done, because you basically go line by line and count. Okay, how many things are on the right-hand side of an equal sign? That tells you how many reads. How many things are on the left hand, and what are the sizes of my loops? That tells you how many writes. And then you can count the number of multiplications and additions, and that gives you the number of flops. So you can get an effective number for your flops, for your bytes, and for your arithmetic intensity. So that's what I show up top. So we have the estimated number of flops in units of gigaflops is 0.34. The number of bytes that are moved in megabytes per iteration is 1.43 megabytes. So it's a pretty small problem. And then so there's your arithmetic intensity. Now, again, until we look at something that tells us what the hardware critical arithmetic intensity is, we don't know if that's memory bound or compute bound. So our do concurrents, let's look at these first. So our split version we're at 4 gigaflops a second and then 16 gigs per second. That's actually quite low. Like I said, this is not a great implementation for CPU. What I mean, how I know that's low is if you run the stream benchmark, for example, that will give you an idea of what your sustained memory bandwidth is, or what your system's sustained memory bandwidth is. And usually you want to compare to that to get an idea of how low this is. But yeah, order 10 gigabytes per second is quite low. You should be closer to like order 100 gigs if you're hitting peak memory bandwidth. So at any rate, these are kind of low. There's definitely some room for improvement there. The HIP kernel, our naive HIP kernel, you can see a huge improvement. I mean, that's 2 orders of magnitude there in difference, and that is a function of the hardware for sure. I mean, GPUs are meant for doing these kinds of operations with tightly nested loops. We're at 412 gigaflops per second and 1700 gigs per second, which is quite nice. Here's our HIP kernel using Bloss. We're at 308 gigabytes per second. Again, effective bandwidth and effective flops, so quite low in comparison to our handwritten kernel. And anyways, I could go through this all day and kind of just talk through these results. What I wanted to show you is Omniperf, and so I'll just show you briefly how you can use Omniperf, and then I'll just switch back over to the slides to show you some of the results we got out of it. Yeah, once you install Rockham, it's pretty straightforward to set up Omniperf. I think in the slides I have some links to their documentation. Let me see if I can find my Omniperf cheat sheet, or I could just Control R my way through this. So Omniperf, you use Omniperf in 2 stages. First is called the profiling stage. It goes through and actually collects all the metrics that are necessary to characterize your application in terms of like the hardware functionalities that you're using. And in fact, it does on the Instinct cards particularly, you can get access to the flop counters and the number of loads and stores from HBM memory into L2 cache. All that stuff gets collected in this first stage. Let me make sure I'm calling the right kernel here, or the right program. So you basically run Omniperf profile. You give the case that you're working on a name. Here, I'm just going to call it Divergence. And it's going to take... Oh, I think I need to activate my Rockham environment. And then we're good. Yeah, so on our systems, we have multiple flavors of Rockham available, so we don't... yeah, you just got to make sure you're in the right environment. So basically what it's going to do is it's going to replay the code a bunch and get all the metrics out. And once you have the profile results, you just run Omniperf analyze on that case, and it will spit out all the metrics like achieve bandwidth and achieve flops. And then you also get a nice chart. It's called the speed of light diagram. It tells you where you are relative to the sustained peaks of performance. Now, the sustained peaks, what Omniperf's pretty cool is under the hood, they do provide a ton of micro benchmarks that if it does not have information about sustained peaks for your platform, it will run those micro benchmarks for you and get empirical measurements of the sustained peaks, which is great. So I'm going to let this run, and while this is running, we're going to go ahead and switch back here because I want to just show you some of the results. Let's do that. Let's slideshow it. So here's the bulk runtimes that came out from our command line stuff. So those benchmarks, which you can find on our self mini apps repository, it will spit out CSVs, and then like you can go through multiple polynomial degrees and kind of stack all the results together. This is looking at polynomial degree 7 for the 2000 element run for 7 variables. This is showing runtime. So lower is better, right? More runtime means I'm waiting longer for my answer. So down, of course, on the bottom, we have our do concurrence and this is using 8 threads for our do concurrence. And then all the way up here is we have our best performing kernel is the HIP kernel, the naive one using shared memory. Now, again, that one was the most performant, but it was limiting in the sense that we can only go up to polynomial degree 7 because of the way we're using shared memory. Now the split kernel, you do take a performance hit, but if you have bigger problems, those are actually I would say quite reasonable to do. They came in second place in terms of runtime. If we turn around and look at the effective gigaflops, so the flops per second, it's another way to look at the same thing we just saw. This tells you where you're at. Higher is better in terms of compute performance. And then we also look at bandwidth, memory bandwidth, actually, and I'll show you in the next couple slides here. We do have roofline diagrams for all of these. The effective memory bandwidth is what we're looking at now. If I think about HBM bandwidth on the MI210 GPUs, now what the vendor reports for the peak memory bandwidth is, I think, 1.6 terabytes per second. And in practice, the sustained number that I've seen quite a bit, just using things like GPU membench, is the SEM Fortran ASCII art in the headers. I may join this. Dude, I'm amazed what you can do in Fortran. People tell me you can't do. I'm glad you like that. Yeah, so the sustained bandwidth that I've seen from like things like GPU membench is like 1.2 terabytes per second. So usually when I think about where I'm at in terms of memory bandwidth, I kind of line that up with that on the MI210s. Now our HIP kernel using shared memory, you can see we're well above that from our effective bandwidth measurements at 4.5 terabytes per second. And then that is particularly because we are using shared memory, but I guess it's not a fair measure because most of our operations are done out of shared memory at that point. Yeah, down below, if I just use my split kernels, we're at about 1.3 terabytes per second, and then our HIP kernel naive with no shared memory, I mean, we're just shy of what I would call sustained bandwidth. But again, our HIP kernel and the HIP Bloss, the HIP kernel split particularly is quite low without using shared memory, and HIP Bloss is right about the same level of performance. All right, so I'm going to show a couple roofline diagrams here. On the left, we're looking at the HIP kernel naive, so not using shared memory. And on the right, we're looking at naive plus shared memory. So let's focus on the left side first here. So again, as I said, as I alluded to before, on these roofline diagrams, you have multiple roofs. So this purple one here is for our HBM, so global memory on the GPU. The red is for our L2 cache. Our green is for L1 cache, and the L1 caches sit on each of the compute units. And then our purple is for shared memory, so local data share. There are two different peaks that are shown in this diagram. I don't know why they're showing FP32 because all my operations were FP64, but okay. I think the FP64 and FP32 peaks are the same on the MI210, so I guess it doesn't matter. But they have one for vector ALUs, so this would be your vector FMA peak. And then because that hardware also supports matrix FMAs, you have a matrix FMA peak, which is a little bit higher. Now, our code is only using vector FMA, so I would only think about that lower one. Now, what I've done in this example is I've tweaked the code just a bit so that it's only running the naive HIP kernel, and that's why you see various dots. Now, it's a little confusing to me still, like what they're doing here on these diagrams, but I'll try to explain in the best way I can what I understand. You have these purple dots, you have red dots, and you have green dots. These like light purple dots are the arithmetic intensity as measured by taking the total number of flops that are counted by the hardware counters and dividing by the total amount of memory that has been moved between HBM and L2. That gives you one measure of the flops per byte. Now, the other measure of flops per byte you can get is if you look at how much data is read and written from L2 further up into the memory hierarchy. That's the red dot. That's the AI L2. And then you have the green line, which is telling you the flops per byte for everything read out of L1 cache, presumably into registers, or from registers into L1. Now, for each one of these, my green dots really ought to be close to my green lines if I am efficiently using L1 cache. My red dots need to be close to my red line if I am efficiently using L2 cache. And my purple dots need to be close to my purple line if I'm efficiently using HBM memory. In the HIP kernel naive case, what this diagram would then tell me is, one, I'm using L1 cache quite well, but my L2 cache usage is quite poor. And in fact, I'll if I have time, I'll switch back to the other panel and show you the L2 cache hit rate for the HIP kernel naive. But the cache hit rate for that kernel is like 50%. It's quite bad. But that's why those red dots are quite far away from the roof that we're getting there. And that's potentially something that's limiting performance. The purple dots, they're not too far from HBM, but they're not as close as I typically like to see things. Still indicative that I'm not reading out of HBM contiguously, so I'm not really getting coalesced memory accesses. So if in theory, HIP kernel naive, the way to improve its performance is to fix our usage of L2 cache. Now, the other thing to see here is look at where our arithmetic intensity is, as far over to the right as you can possibly get. If I were to go up on this diagram, what it tells me is what my peak performance would be at that arithmetic intensity. So if I consider this dot, which is right around 1 flop per byte, that puts me just above 1,000 gigaflops per second, which again, I would be okay if I got just over 1,000 gigaflops per second, even though what the vendor reports is 21,000, but that's because my application's memory bound. So that's kind of the goal that I would shoot for in terms of like making sure my performance was as best as I can get on this hardware. Now, if I go over to the shared memory case, now remember, shared memory is nice because we have contiguous memory accesses. We load from HBM in a contiguous way into shared memory, and then we do strided access out of shared memory, which is fine. I know it's hidden here, but our L2 dot is sitting right underneath that purple dot, so we're still not, for some reason, using L2 cache very well, but our purple dot is a lot closer to the HBM roof, which is good. Suggesting that we are pretty close to that 1392 gigabytes per second according to the profiler. And because we've moved things into shared memory, I think if I recall this one, the cache hit was like something like 60%. It wasn't as bad as like 50. But because we're doing things out of shared memory, the number of bytes that we're actually loading out of HBM has gone down. So I've effectively improved my arithmetic intensity by moving things into shared memory. So instead of being stuck near arithmetic intensity of 1, I've moved over to the right a little bit because of using shared memory, and because things are a little bit better in terms of cache usage, I've gone up towards that roof. And to be honest, I'm quite okay with this. I mean, hitting basically 2 teraflops for a GPU for that kernel is quite huge for us, and certainly in comparison to where we had been, which is more like 200 gigaflops. So factor of 10 over where we started. Now, this was my point, and Nicola, I hope this maybe addresses the question you asked about intrinsic matmul versus Bloss, but this is what we looked at. So in our implementation, gem is a big part of the computational workhorse there. The same kinds of behavior we see bear out in HIP Bloss gem v strided batched. What we're looking at here is if I call gem with m rows by m columns for the first matrix, and the second matrix is m rows by m times n columns. Okay, so if I go from the bottom here, I have basically the width of that second matrix is 1,000, and then up here it's 100,000. So we're getting wider matrices as you go up to the top on this diagram, and as you go from left to right, we're increasing the number of rows, which is equivalent in self to increasing the polynomial degree for your derivative matrix. Where we sit for all of our benchmarks is in this range. polynomial degree 7 through 11, which is 8 rows up to 12 rows. This is kind of where we're looking at, and what we're showing on these diagrams is the achieved bandwidth for Bloss gem for those matrix sizes. And you could see that the relative to the peak, right, or the sustained peak, which is around 1200 gigs per second, the effective bandwidth here for these smaller matrix sizes is quite far away from the peak. But of course, as you increase the number of rows, particularly for the FP, I mean, all of them go up in terms of bandwidth, and we get closer to that peak. But it just, what this tells me as out of the box is that, like, for our problem, it's not that Bloss is bad or HitBloss is bad. It's just the developers of Bloss and HitBloss are not thinking about small matrices like this. They're not thinking about spectral element methods in the way that we are. And it's just not suited for our problem. That's all it means. It's not optimized for small matrices. And, you know, in practice, yes, if someone says, look, you should probably use a library, sure, you can do that. But I don't like telling people, or I don't like being told that that's the only way to do things. So if you're out there and you have told me this in the past, I hope this message is landing with you. I know you're out there. I do want to make a couple of plugs for some other things we've got going on. So that's about the gist of what I wanted to talk about today. Is here's a bunch of ways to do it. Yes, you can use a library. That's great. Or you could do it yourself and use the knowledge you have of the algorithm to really make things scream on this hardware. We got some new stuff coming out. Garrett has done some really cool work to really help build some of the workflow side of doing conservation law solving. We've been kind of hashing around some ideas on how you can go into like Inkscape and draw your boundaries for your domain and get that into a mesh generator. So the mesh generator we're looking at is called HokeMesh. It's a project from David Kopriva, Andrew Winters, and the folks over at Trixie Framework. Amazing tool. It does it generates isoparametric elements, quads in 2D and hexes in 3D, so it's quite compatible with what we're doing. I mean, surprise, surprise, I learned spectral element methods from David Kopriva, so there's a reason all these things mesh well. So the idea behind SVG to HokeMesh, which we just made public today, is that, yeah, you can draw your domain in Inkscape and export the SVG into a HokeMesh control file. And that HokeMesh control file you can use to then generate a mesh. And we've got a number of examples up there. And in the coming weeks, we'll be having a number of tutorials just showing how you can generate meshes, because that is literally the first step in doing your problem. Once you have your mesh, getting it into self is the next layer, and then of course having the conservation law solver available to run your simulation on that mesh is the next part. So we're actively building out curricula or tutorials that focus on each of those steps of the simulation workflow. Check out that repository, give it a shot, see what you think. Also check out HokeMesh, great tool for generating spectral element meshes. The last live stream I did, I had someone ask about Open Collective. There was some mention that Open Collective was dissolving, and they were asking like whether or not we're still going to be up there. So let me make a few clarifying remarks here. I'm actually going to go, if you want to look at it yourself, the link is here. I will put the link in the description below. But essentially what the deal is you need to understand there's a few different platforms here. So there's Open Collective Foundation, which was what is called a fiscal host on the Open Collective site. And that fiscal host hosted a number of public open source projects, which unfortunately for a lot of those open source projects, they either had to spend down their money or transfer to another fiscal host. Fluid Numerics is set up as its own fiscal host. So the Open Collective site will still be there going forward. Fluid Numerics is its own fiscal host. So when you make donations to the Fluid Numerics open source projects like Self on Open Collective, those go directly to us so that we can pay for GitHub. We can pay for our energy costs and our facilities to be able to do this kind of work, to pay salaries to make this code happen. And of course, we have a long-term vision of trying to enable other contributors to be able to be paid for their time and helping us solve issues and test things out. All of that stuff is still possible. Open Collective for us is not going away. So I did want to make sure that you guys got some clarification on that. So with that being said, again, I'll make another plug. Please, please, please consider becoming a backer of our projects. If you think you can do that, that'd be great. If not, again, subscribe to the channel, give us a like here, give us a star on GitHub, use our code, open up issues, do amazing science. If you have models that you want to see implemented using Self, we're taking requests. we'll implement them for you and let you know when they're ready, so you can kick the tires with solving your problems. Next week, I'll be talking about the linear and nonlinear Euler equations, which we're getting implemented. We're just about wrapping that up. So we'll be talking about that next week. We've got shallow water equations coming up soon. And I've got some notes in my notebook about doing Maxwell's equations, so we'll have some electromagnetism stuff as well. If there's anything else you guys are interested in, I've already got one request for sediment transport. Drop it in the chat now or in the comments below the video. We do take those to heart. Or you can go to the Self GitHub page and open an issue. Tell us what you want to see implemented in the code. I'll hang here for a few minutes. If you guys have questions, go ahead and drop the questions in the chat. It can be about anything we talked about today. It doesn't have to be. If there's just anything you want to talk shop about, that's what I'm here for. Oh yeah, Nicola, I hope you know you can also do like UTF-8 characters in Fortran. I didn't think that was possible before, but yeah, that's doable too. Well, awfully silent today. Nonetheless, everyone who tuned in, thank you so much. Those of you who are watching after the fact, thank you so much. Oh, what are your thoughts on collocation? It's quick and dirty, and it gets the job done. You still need a way, if you're doing collocation, you're really thinking about a spectral method, so a single element domain, in my experience. I could be wrong. Yeah, collocation's fine. But the reason I like DG is it opens up, so like a weak form, least squares approach, is it because you separate out volume fluxes, volume flux divergence from the surface fluxes, you can do coupling between subdomains, which is essentially each of your elements. And so it opens up the flexibility of using unstructured grids. In my experience, collocation is it's structured grid and single element, so high polynomial order typically. But to be honest, I haven't used them in practice too much to know. Maybe I'm missing a creative approach here that you could do with collocation that you can't do with weak form DG. I guess I'll hint, since we're talking about various spectral methods here. I have some old code that I'm resurfacing. I'll be bringing out into Self probably early next year to do continuous Galerkin, so we can do elliptic problems in 2D and 3D. Particularly, we want that so we can do incompressible fluid solvers, things like that. Yeah, those are I would say those are my thoughts on collocation. Is they're fine. They're really easy to implement, but they're generally in the ways I've used them, used for single element domains, but high polynomial order. So in my experience, just not as flexible as something that can do multi-domain. Yeah. If you have other questions, you can always reach out to support@fluidnumerics.com. If you are a collaborator, the bottom end. I mean, I think I even have a backer on our Fluid Numerics open source page that's not even doing the $50 a month. We have a Slack channel that's got all of our collaborators as well as myself and Garrett on there, and you have unfettered access to talk to us at any time about this, about any of your projects you might need help with, any kind of coding questions. Fortran, non-Fortran related, GPU, non-GPU related. We just want to help create a community that's really focused around doing scientific work on new hardware. We'd love for you guys to be a part of it. At any rate, you can reach me at support@fluidnumerics.com. You can drop comments below. You can open up issues on our GitHub pages. But definitely check out SVG to HokeMesh. Check out Self. And I guess I'll see you guys next Thursday to talk about Euler equations implemented with Self. Thanks for tuning in. Talk to you later.